Welcome back. This is section 11.6 on phase diagrams. A diagram is a picture that makes it easy to understand lots of numbers. So I think this is actually easy. I can see this very simple. What you have to remember is that if you have a temperature change, you might have a change of state. So for instance, if a temperature goes from one temperature up to another temperature, you might have something melt. Or if it goes down, you might have something freeze. Or if it goes up a lot, you might have it melt and then boil. But there's another thing going on except just temperature. There's also pressure. For instance, if you go ice skating, the reason you can slide on the ice on ice skates is because the pressure of your body weight pushing down on a thin blade of steel on ice melts that ice, but it only melts it only under the blade. So what you're actually skidding on is water. It's like you're hydroplaning. But as soon as you leave, the surrounding ice is so cold that that little band of water freezes again. And that's what the little line that you see after you've passed when you're ice skating. You make marks. Those marks are refrozen little beads of water, but the water was because at your pressure, it wasn't cold enough to melt the ice or freeze the ice. That means that different pressures can make something either boil faster or slower, or freeze longer or freeze faster. You can also have pressures that will make solids go directly into gases. They won't even melt into liquid. We see that when you have dry ice. Dry ice doesn't melt into liquid carbon dioxide and then again go into vapor. It goes straight from solid into liquid at a certain or into gas at a certain temperature. That means that anywhere that I want to go from to, I can find out what state it is at a certain temperature and a certain pressure. So along the bottom, I've got temperature. Okay, this is temperature here, and it's going higher this way. Pressure is going higher this way. So if you increase pressure, you're going to change solids, liquids, and gases in two directions. So it's two-dimensional, temperature and pressure. So over here on the left, this is all solids. In the middle is liquids. Over here on the right is gases. So that makes sense. The higher temperatures, normally you would have gas. Lower temperatures, you would have liquids, and then even lower temperatures still, you would have solids. But you're going to see that the pressure can change all those numbers a lot. So the first the number line that we're going to look at, this line is from the triple point, which is T, right here, to the critical point, which is C. Okay, so from the triple point to the critical point, this is where liquids will go into gases. So if you were, if the pressure is the same, whatever pressure you're looking at, if you go to that line and go further to the right, which means you're increasing temperature, you will boil. You will go from a liquid to a gas. If you go backwards from a gas to a liquid, you'll condense at that pressure. If you go higher in pressure, so if I were looking here, it would be at this point right here, if I would go right, more temperature, then I have gas. If I go to the left, I have more liquid, okay, at that pressure. But if I go to a higher pressure, it boils at a higher temperature. The higher the pressure, the more the boiling point. That's the reason why brownie mix has high altitude directions. If you live high in the mountains, like in the Rockies, your brownies won't bake at the normal time that you're supposed to do. The directions say leave it in at this temperature at this amount of time. If you were to take the brownies out at that amount of time, they wouldn't have finished baking yet. The reason why is because all of the boiling point of the liquids that's in those brownies haven't actually come out as steam yet because it's higher pressure or it's lower pressure, and so it takes longer to cook. The higher the pressure, the quicker it takes to cook. So that's why if you have a hot pressure pot, miracle pot or whatever it's called, You can make food much faster because it gets hot faster and goes to a higher temperature faster. And the higher temperature can cook the food faster. So that's the trick. So this is called the liquid vapor interface, liquid to vapor to gas. The critical point, the C, is a point at which you can't compress gas into liquid. If you go beyond a certain pressure called the critical pressure, and you go on beyond a certain temperature called the critical temperature, anything past that, you have a supercritical fluid. You don't have a gas and you don't have a liquid. You can't compress something into a liquid no matter how much pressure you put on it, and you can't essentially distinguish between liquid and gas at any pressures beyond that. So that's why it's called critical. It's critical because beyond that, you can't have a distinct liquid, distinct gas phase. It's kind of a murky place in there. On the left, the line on the left is the interface between liquid and solid. And this would be melting and freezing. Melting and freezing would be at the same point. So at whatever pressure you choose, if you go to the line, anything past that line will melt from solid into liquid. If I'm going in the other direction, it will freeze. So the freezing point and the melting point are the same. And what you're going to see most of the time, you're going to have a tilted line to the right, which means that the higher temperatures, normally you're going to get liquids. Okay, at lower temperatures, you usually get solids. Okay, we're going to see that water is a little wacky. Water actually is denser as a liquid than it is as a solid. That's why ice floats. And so these shapes change just a little bit with a couple of these ones that have very high bonds or intermolecular attractions. This last line below the triple point is where you cannot have liquids. If you were to increase the temperature from one side to the other of that line, you would go directly from a solid straight into a gas. That's called sublimation. If you go backwards, it's called deposition. You deposit, like say frost. Sublimation is when like your ice cubes shrink or something like that. Now the T is a triple point. The triple point is really cool. It means that at that temperature and pressure, okay, so you have a pressure here, a temperature here. At that point, all three phases exist at the same time. You have solid and liquid and gas. Now it's a very low pressure. So if you were to reduce the pressure, say in a pressure chamber, and you remove most of the air or all the air to where you have pretty close to a vacuum, then at 0 degrees, at the freezing point of ice, that's also the melting point. So you'll have ice there, you'll have water there, but you'll also you'll have gas there. All three, because it's such a low pressure that solid will go straight into gas. So that's called the triple point in the phase diagram. Here's what I was talking about with water. Instead of a slanted line like this, you're going to have a slanted line like this, because there's so many forces because of the hydrogen bonding in water, so many forces that you're actually going to, it changes the pressure a little bit. You're actually going to have liquid at a lower pressure than you would normally have. The last wacky one is carbon dioxide. Carbon dioxide has such a high triple point that you can't have a liquid carbon dioxide unless you have 5 atmospheres of pressure. So if you're just in the lab and we pull out the cookie dough and get some dry ice, it won't turn into liquid. You're not going to have solid turn into liquid and then immediately turn into vapor. It's going to go straight from the solid to the vapor stage, because at room temperature and at 1 atmosphere of pressure, it's way down here, and you're not going to have any liquid carbon dioxide at all.